Hello and welcome to this video on how to determine the number of classes in latent class analysis. My name is Geiser. I'm an instructor and statistical consultant with QuantFish, and on this channel I present weekly statistics tutorials. I usually talk about multivariate statistical methods including factor analysis, structural equation modeling, multi-level analysis, and latent class modeling. If this is something that interests you, please subscribe to this channel. Also, check out the description for additional resources, including workshops that I offer through QuantFish. In this video, I want to talk about how we can find out about how many classes we should retain in a latent class analysis. And this is an issue that is similar to what we face when we run an exploratory factor analysis, where the idea is that we want to determine the number of factors to retain and the number of factors that explain our observed correlations well. And so here we are interested in finding out how many latent classes do we need to appropriately account for the observed response pattern frequencies in our data set. And I want to discuss 4 different criteria that we should think about. So first is the criterion of absolute model fit. Second, we can perform descriptive model comparisons based on descriptive measures of fit for different models. We can also perform tests of significance, so inferential comparisons between different models. And then finally, we should also take into account substantive and theoretical considerations. So let's go through each one of these, and I will show you some examples regarding how we can determine the number of classes. So let's start with absolute model fit. What does that mean? So this means for absolute model fit assessment, we would look at a given latent class model, let's say for example a 2-class model, and we would try to find out, does this model adequately reproduce our observed response pattern frequency? So in other words, are the response pattern frequencies that are implied by the model or predicted by the model in line with the response pattern frequencies that we have observed in our data? And for that purpose, we can use chi-square tests of absolute model fit. Chi-square tests directly compare the observed response pattern frequencies to the model implied response pattern frequencies for a given model, and then we can see whether a model has to be rejected. It shows a significant discrepancy between the patterns that were observed and the patterns that are implied by the model or not. And in that way, we can look at different models, for example, 2 classes, 3 classes, 4 classes, and we can stop when we find a model that shows a decent absolute fit or one that does not have to be rejected by those chi-square tests of model fit. 2 of the most common ones that we use in latent class analysis are the Pearson statistic, which you can see here on the left-hand side, and the likelihood ratio statistic, G², which is shown on the right-hand side. You can see in both of these formulas we have FW and F_W. FW is a particular observed response pattern frequency, and F_W is the corresponding model implied pattern frequency for that same pattern. And so both these statistics look at discrepancies between the observed and model implied pattern frequencies. In large samples, so under asymptotic conditions, both the Pearson statistic and the likelihood ratio statistic should provide similar or very close results given you have a large enough sample. Now in practice, we have the problem that oftentimes we are looking at many items in an LCA or a relatively large number of items, and we do not have such large sample sizes. And then we might run into the issue of data sparseness, because when you have, let's say, 10 or 12 items, there are already a lot of different response patterns that could be observed under a given model, and then the pattern frequencies may not be so high, which could then jeopardize the results from chi-square statistics. That could violate asymptotic conditions, which means either one or both of these statistics may not follow a chi-square distribution in practice. And so that is one issue that we're having with these. I will show you an example here. So this is an output from Mplus, where we get both the Pearson statistic and the likelihood ratio statistic, and you can see that these two values are somewhat similar but not totally similar. The Pearson statistic is 23.389. The likelihood ratio statistic takes on a value of 27.203 here, and so the Pearson statistic is not quite significant, so to say, at the 0.05 level. So you can see the p-value here is 0.0542. So according to the Pearson statistic, we would not have to reject the model, whereas the likelihood ratio statistic has a p-value of 0.0181, which would be significant at the 0.05 level. So according to the likelihood ratio statistic, we would reject the model. Now, obviously, those criteria are arbitrary anyway, and there's not really a meaningful statistical difference between a p-value of 0.05 and one of 0.02. So we shouldn't overinterpret that, but it shows you the general issue that we're having with these statistics, that they may be discrepant, and the more they are discrepant, the more difficult it becomes for us to really say something about absolute model fit. So in conditions where you have data sparseness, those statistics can be very different, and in that situation, you shouldn't trust either one of them. So absolute model fit assessment can be difficult in latent class analysis, which is why many studies focus on relative model fit assessment. So meaning they compare models with different numbers of classes against one another, rather than saying something about the absolute fit of a single model. And in terms of model comparisons, we can, on the one hand, do descriptive comparisons, or we can use statistical tests. I will first talk about the descriptive comparisons, and then we'll see how we can also statistically compare models using inferential statistics. Descriptive comparisons in latent class analysis typically focus on information criteria such as the Ekheik's or Bayesian information criterion, AIC or BIC, and the way that this works is that you estimate models with different numbers of classes, for example 1, 2, 3, 4 and so on classes, and you take the BIC and AIC values from your computer output and you compare them for different models, and you try to see if there's a model that has the lowest value of either AIC or BIC. And so here I did this in the example for the 1 through 4 class solutions. You can see the 1 class model has the highest AIC and BIC, and that's typically the case that this model does not fit because that's the independence model. And so then 2 classes is a lot better. Both AIC and BIC are a lot lower for 2 classes. For 3 classes, the BIC is even lower, and also the AIC, and then for 4 classes, there's not much of a change in AIC, but the BIC goes back up. So this would then lead us to conclude that we should retain 3 classes according to the BIC, because the BIC value is lowest for 3 classes. The AIC is not fully conclusive, and that's a typical result. So with AIC, we often see that it declines further even as you add additional classes, but at least you can see there's not much of a difference between 3 and 4 classes here anymore. So we could go with the 3-class solution based on the BIC. The BIC also has been shown in simulation studies to be a good indicator of class enumeration. Now this is really straightforward, which is why I like this procedure with the information criteria. In my experience, often the BIC is a really good indicator for a parsimonious solution that also often makes sense. However, this of course is not a statistical test, so these are purely descriptive. It's not clear what difference in BIC values would be statistically meaningful, when should we really interpret that as a difference versus not, and some people don't like this or don't like those indices for that reason. They want to have a statistical test. And so there's also the possibility of statistically comparing different latent class models using inferential statistics, meaning tests of significance, and that can be done because latent class models with different numbers of classes are nested models. And nested models can be compared using likelihood ratio difference tests, also known as chi-square difference tests, using the difference in the likelihood ratio chi-square values, or delta G squared. Now, of importance, you cannot do this with a Pearson statistic. So when you do these difference tests between models with different numbers of classes, they have to be based on the likelihood ratio statistic, not the Pearson statistic. And there's one additional complication, and that is that the model with one fewer class is a special case of the model with one more class. However, it follows by setting one of the class probabilities to 0. And 0 is a boundary value for probabilities, which is why this is somewhat complicated for a chi-square difference test, because then the delta G squared may not follow a theoretical chi-square distribution because of that boundary constraint. And so the way we address this is that we do not compare our chi-square difference value or likelihood ratio difference value to the theoretical chi-square distribution, but rather we use a parametric bootstrap procedure to generate an empirical distribution of the likelihood ratio chi-squares, and then we compare our empirical likelihood ratio to that bootstrap distribution. So let me explain to you in a little bit more detail how that works, because it is a little bit complicated. So the first step is that we estimate the model with C classes and the model with one class less, which would be the C-1 class model, for our actual data, and we compute the delta G squared, meaning we take the likelihood ratio for the, for example, 2-class model, and we subtract from that the G squared value for the 3-class model, which tends to be lower, or would be at least, or would be at most as big as the one for the 2-class model. So we take the difference between the two models in their likelihood ratio statistics, and then in the next step we use the model with one fewer class, for example the 2-class model, as a population model, and we draw bootstrap samples from that model. So we basically run a simulation where we draw from our 2-class model, and for example we do that 1,000 times, and then in these 1,000 bootstrap samples, we fit both the C-class model and the C-1 class model. And again, we compute the chi-square difference for each bootstrap sample. So 1,000 times we have a difference then. And that yields an empirical distribution of chi-square difference values under the null hypothesis that the model with one fewer class is the true model. So for example, the 2-class model. So we're basically generating a null hypothesis empirical chi-square difference score distribution that we can then use to compute an empirical p-value for our delta G squared from step 1. So that's what we're doing in step 4. We're taking our empirical chi-square difference value for the actual data, and we compare it to the bootstrap distribution, and then we can see where does our empirical delta G square value fall relative to all those that were obtained in the bootstrap. And then if our value looks like it is pretty extreme compared to the distribution, then we would reject the null hypothesis. So specifically, when the p-value that we obtain is smaller than or equal to alpha, so when our delta G squared value belongs to the 5% of the most unlikely or most extreme difference values compared to the bootstrap distribution, then we would reject the null hypothesis that the C-1 class model fits as well as the C class model. So then the model with one fewer class would be rejected. That all sounds complicated, but the good news is that you don't have to do this manually. Computer software programs such as Mplus or LATENT Gold do all this behind the scenes for you, and all you need to do is take a look at the p-value in the output. So here's an example from Mplus. In this case, I fit a 2-class model and a 3-class model. The 2-class model would be the one under the null hypothesis, so that's the C-1 class model. And Mplus then gives us the log likelihood value for the 2-class model, H0, and 2 times the log likelihood difference. And 2 times the log likelihood difference is the delta G squared. So that's our chi-square difference value for which we want to obtain the p-value. The difference in the number of parameters between the 2 and the 3-class model in this case was 6, and that gives us the degrees of freedom for our difference. Next is the approximate p-value, which is based on 1,000 successful bootstrap draws in this example, and you can see the p-value here is very, very small, smaller than 0.0001. So therefore, the 2-class model can be rejected in favor of the 3-class model, or we might say the 3-class model fit significantly better than the 2-class model. Now with this criterion, you would go ahead and you would next test the 3-class model against the 4-class model, and then see if the 4-class model still fits significantly better than the 3-class model, and you would stop once you obtain a non-significant p-value for this parametric bootstrap test. Now this has the advantage that it is a more stringent criterion than a BIC value, and there's a statistical decision criterion that you can set a priori, where you say my alpha level is, for example, 0.05, and I'm going to reject if it's smaller than or equal to 0.05 later on. So that's a little bit more stringent. However, it also comes with disadvantages. For example, when you have a large sample, then there will be a lot of power for this bootstrap test, and you may end up with many, many more classes than you would have with just the BIC criterion. So the BIC criterion tends to favor more parsimonious solutions, whereas this bootstrap has a tendency in practice to go for models that have a larger number of classes. And then finally, we should also take into account substantive considerations when we make a decision about the number of classes. And the first, maybe most important substantive consideration here is whether a solution is trustworthy. I mean, it doesn't make any sense to say, oh yeah, 6 classes are great according to BIC and the parametric bootstrap likelihood ratio test, but in a 6-class model you have classes that make no sense, or you have lots of boundary parameter values, or you have other estimation problems that make a solution untrustworthy or otherwise undesirable. So you should also make sure that the solution really is one that is interpretable and trustworthy. So all classes in the model should be meaningful and they should be interpretable. And also one consideration is whether additional classes are merely variations of earlier classes. So if you have just a bunch of ordered classes that get added to the model that have the same general shape as previous classes and wouldn't be interpreted in a very different way, then it is questionable whether those additional classes are needed in order to summarize your data. And it of course also depends on your goals, so to say, what you want to achieve, but that's also something that we want to consider. We want to be parsimonious typically. We don't want to explain 12 different latent classes to our audience. That would be very complicated. So less is more typically. So you also want to take that into account, whether these classes map onto your theory about typological differences and whether they make substantive sense. I hope you found this video useful to learn about how to determine the number of classes in latent class analysis. Don't forget to subscribe to this channel and to check out the description for additional resources, and I'll see you next time.